Strap in, cosmic detectives, as we plunge into the mind-boggling mystery of the Fermi Paradox. Why, in a universe teeming with stars, haven't we found a single trace of alien civilizations? Welcome to an electrifying journey through the galaxy, where we'll unravel the enigma of cosmic silence, exploring the science, theories, and profound questions that make us wonder if we're truly alone. What's stopping us from hearing alien signals? Are civilizations out there, hiding or extinct? And what does this silence mean for humanity's future? Get ready for an epic adventure that will spark your imagination and leave you buzzing with curiosity. Let's dive into the Fermi Paradox together. Picture the Milky Way, a swirling spiral of 100 to 400 billion stars, each potentially hosting planets where life could thrive. Now zoom out to the observable universe, with its 2 trillion galaxies, each brimming with billions of stars, stretching across 93 billion light-years of space. The numbers are staggering, the possibilities endless. Yet, in all this vastness, we've detected no signs of intelligent life, no radio broadcasts, no interstellar probes, no cosmic megastructures blotting out starlight. This glaring absence is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who in 1950 casually asked his colleagues over lunch, "Where is everybody?" That simple question has haunted scientists, philosophers, and dreamers ever since, forcing us to confront the possibility that we might be the only thinking beings in the cosmos. But why? What could explain this deafening silence? Stick with me as we peel back the layers of this cosmic riddle, from the birth of stars to the fate of civilizations, and see if we can crack the code of the universe's greatest mystery. To understand the Fermi Paradox, we need to start with why we even expect aliens to be out there. The universe is ancient, clocking in at 13.8 billion years old since the Big Bang. Stars began forming just a few hundred million years after that explosive beginning, giving life plenty of time to emerge, evolve, and perhaps build civilizations. Our own Sun is a relative youngster at 4.6 billion years old, meaning countless stars have had billions of extra years to host life-bearing planets. The discovery of exoplanets, planets orbiting other stars, has exploded our expectations. Since the first confirmed exoplanet in 1992, we've catalogued over 5,500, with missions like NASA's Kepler and TESS revealing that nearly every star has at least one planet. Conservative estimates suggest there are billions of Earth-like planets in the Milky Way alone, many in the habitable zone where liquid water could exist. Add in the fact that life on Earth appeared remarkably quickly, within about 300 million years after the planet cooled enough for oceans, and it seems like the galaxy should be buzzing with activity. So, where are they? This tension between expectation and observation is the paradox's core, and it's what keeps astronomers up at night, scanning the skies for any whisper of extraterrestrial intelligence. Let's turn to the Drake equation, a mathematical framework that puts numbers to this expectation. Developed by astronomer Frank Drake in 1961 for the first SETI meeting, it estimates the number of communicative civilizations in our galaxy. The equation is n equals r asterisk times fp times ne times fl times phi times fc times l, where r asterisk is the rate of star formation, about 7 new stars per year in the Milky Way, fp is the fraction of stars with planets, now estimated at nearly 1, thanks to Kepler, ne is the average number of habitable planets per star, perhaps 0.2 to 1, based on recent data. FL is the fraction where life emerges, unknown, but Earth suggests it's not 0, phi is the fraction where life becomes intelligent, even murkier, as Earth's path from single cells to sapiens took 4 billion years. Fc is the fraction that develops communication technology, like radio, and L is the lifetime of such civilizations, could be 100 years or 10 million. Plug in optimistic numbers, and N could be thousands or millions. Pessimistic ones drop it to less than 1. The equation isn't a crystal ball, it's a way to organize our ignorance, but it highlights how even modest assumptions lead to a crowded galaxy. If N is high, why no contact? This is where the paradox bites, prompting us to question each factor and imagine what could go wrong. Now, let's talk about the search for these missing aliens. The search for extraterrestrial intelligence, or SETI, has been our main tool since the 1960s. It began with Drake's Project Ozma, which used the Green Bank telescope to listen to two nearby sun-like stars, Tau Ceti and Epsilon Eridani, at the hydrogen frequency of 1420 MHz, thought to be a universal water hole for signals. No luck, but it sparked a movement. Today, SETI uses arrays like the Allen Telescope Array in California, with 42 dishes scanning the sky for narrowband radio signals, tight frequencies that nature doesn't produce, a sign of technology. The Breakthrough Listen project, funded by billionaire Yuri Milner, is scouring 1 million stars and 100 galaxies across billions of frequencies, using AI to sift through the data noise. They've even checked for optical signals, like laser pulses that could carry messages faster than radio. Yet, despite billions of dollars and decades of listening, the results are zilch. No repeating signals, no patterns that scream intelligence. The famous 1977 WOW signal, a 72-second burst from Sagittarius detected by Ohio State's Big Ear telescope, matched what SETI dreams of: strong, narrowband, and at the hydrogen frequency. But it never repeated, and follow-ups found nothing. Was it a comet, a satellite, or a one-off alien broadcast? The mystery lingers, but it's the closest we've come, fueling hope amid the silence. Beyond radio, SETI has expanded to techno-signatures, indirect signs of alien tech. Dyson spheres, hypothetical megastructures encasing stars to harness their energy, would dim starlight in infrared, detectable by telescopes like WISE. Waste heat from advanced societies could glow in mid-infrared, as searched by projects like Jihad. Atmospheric pollution, like chlorofluorocarbons, might show in exoplanet spectra, a fingerprint of industry. Even artifacts in our solar system, probes or ruins on the moon, could be lurking, though searches like Lunar Reconnaissance Orbiter images show nothing. The paradox persists: if aliens are common, their tech should be visible, yet the skies are empty. This lack pushes us to creative explanations, from biological barriers to sociological twists, each more intriguing than the last. One of the most compelling solutions is the rare Earth hypothesis, detailed in the 2000 book by paleontologist Peter Ward and astronomer Donald Brownlee. They argue that while microbial life might be common, complex life, like animals, plants, and especially intelligence, is extraordinarily rare due to Earth's unique features. Start with our planet's position in the solar system, in the habitable zone where water is liquid, not too hot like Venus or too cold like Mars. Earth has a large moon, formed from a giant impact 4.5 billion years ago, stabilizing our axial tilt to prevent wild climate swings. Plate tectonics, driven by a hot core, recycles carbon, regulating temperature via the carbon silicate cycle. Volcanoes release CO2, weathering absorbs it, keeping Earth temperate for billions of years. A magnetic field, generated by the liquid outer core's dynamo, shields us from solar wind, preventing atmospheric stripping like Mars suffered. Jupiter's gravity deflects comets, reducing catastrophic impacts after the late heavy bombardment. Even our galaxy's location matters, in a quiet arm, away from the radiation-heavy center or supernova-prone spiral arms. If any of these are missing, complex life falters. On Earth, single-celled life dominated for 3 billion years. The Cambrian explosion, 541 million years ago, brought diversity, but intelligence arrived late. If this chain is rare, the galaxy might be full of slime but empty of starfarers. Doesn't that make our existence feel like a miracle? Building on rare Earth is the Great Filter concept, introduced by economist Robin Hanson in 1998. This posits a step in the evolutionary ladder so difficult that most worlds never pass it. The filter could be early, abiogenesis, the jump from chemistry to self-replicating life, might require improbable events, despite lab experiments like Miller-Urey synthesizing amino acids from primordial gases. Panspermia, life hitchhiking on meteorites, might spread microbes, but the spark itself could be a cosmic rarity. Or the filter is the leap to multicellularity, which took 3 billion years on Earth, or to intelligence, needing big brains, tools, and social cooperation. If the filter is ahead, we're in trouble. Advanced civilizations might inevitably destroy themselves through nuclear war, pandemics, climate catastrophe, or superintelligent AI gone rogue. Earth's close calls, the Cold War's brinkmanship, global warming's tipping points, suggest we're approaching such a filter. If behind, we're pioneers, the first to cross, with a galaxy to claim. This idea turns the paradox into a warning: survive the filter, or join the silent majority. Can you sense the urgency in this cosmic bottleneck? Another intriguing explanation is the zoo hypothesis, proposed by astronomer John Ball in 1973. This suggests advanced aliens exist but deliberately avoid contact, treating Earth as a zoo or nature reserve, observing us from afar without interfering. Perhaps they have a galactic code, like the Prime Directive in Star Trek, forbidding interaction with primitive societies to allow natural development. They might use cloaking tech to hide their presence, or monitor us with stealthy probes disguised as asteroids. This assumes a universal ethic among aliens, a coordinated effort to quarantine emerging worlds. Evidence. None direct, but UFO sightings, if real, though most are debunked, could be leaks in their system. The hypothesis solves the paradox by making aliens invisible by choice, but it's hard to test. How do you prove hidden watchers? Still, it offers a hopeful spin: we're not alone, just not ready for the club. Could extraterrestrial ethnographers be studying us right now? Shifting to a darker tone is the dark forest hypothesis, popularized by Chinese author Liu Cixin in his novel, The Three-Body Problem. In this view, the galaxy is a dark forest, where civilizations are hunters, silent and paranoid, knowing that revealing themselves invites destruction. Resources are finite, and advanced aliens might see others as threats, preemptively eliminating them to secure survival. Game theory backs this. In an uncertain cosmos, the safest strategy is stealth: don't broadcast, don't colonize visibly, lest you attract predators. Earth's radio signals, leaking for over a century, might be a beacon for doom, though they've only reached a 200 light-year bubble, a galactic speck. Aliens could use subtle tech, like quantum communication or gravitational lenses, undetectable to us. This hypothesis explains silence as a survival tactic, turning the paradox into a horror story. It warns against messaging extraterrestrial intelligence, like the 1974 Arecibo message or Voyager probes, which some scientists, including Stephen Hawking, called risky. Are we naive newcomers in a predatory galaxy? Let's consider biological and evolutionary factors. Life on Earth shows that intelligence isn't inevitable. For 3.5 billion years, microbes dominated. The evolution of eukaryotes, cells with nuclei, took 2 billion years, requiring endosymbiosis, a cell engulfing another to form mitochondria. Complex life exploded in the Cambrian, but mass extinctions, like the Permian 251 million years ago killing 96% of species, reset the clock. Intelligence arose in hominids, driven by tools, fire, and social brains, but dolphins and octopuses show it's not unique, yet only humans built radio. If evolution favors survival over smarts, most planets might host clever animals but no engineers. Convergent evolution, eyes or flight arising independently, suggests intelligence could emerge elsewhere, but the path is narrow. The paradox might stem from life's commonality but intelligence's rarity. Could the galaxy be full of dolphins but no Einsteins? Galactic geography plays a role too. The galactic habitable zone, a ring 20,000 to 30,000 light-years from the center, balances heavy elements for planet building and low supernova risk for stable biospheres. The core's density bathes worlds in radiation, sterilizing life, while the outskirts lack metals for rocky planets. Our sun's position is ideal, but if habitable zones are patchy, civilizations cluster in pockets, far from us. Supernovae or gamma-ray bursts could wipe out life periodically, resetting evolution. A nearby burst, like one 2,500 light-years away, could devastate ozone, causing extinctions. If such events are common, intelligent life rarely lasts long enough to contact us. Doesn't this make our quiet corner feel like a safe haven? Technological and communication barriers offer practical explanations. Radio waves, our SETI focus, might be a brief phase. Civilizations advance to lasers, neutrinos, or quantum entanglement, signals we can't detect. The L-band, water hole, 1 to 10 GHz, quiet for natural noise, is our guess, but aliens might use different bands. Signals degrade over distance, interstellar dust scatters them, and power requirements for galaxy-spanning broadcasts are enormous. A civilization might send targeted pulses, missing Earth. Our search is limited. SETI scanned less than 1% of stars at meaningful depths. The Square Kilometre Array, coming online, will boost this, but we're still dipping toes in an ocean. Could we be using the wrong cosmic phone? The transcension hypothesis, proposed by futurist John Smart, suggests advanced civilizations transcend physical space, migrating inward to black holes or simulated realities where computation is denser and faster. Near singularities, time dilates, allowing immense processing in moments. They abandon expansion for introspection, their signals vanishing into event horizons. This solves the paradox. Without death, aliens evolve beyond our detection. It echoes singularity ideas in AI, where minds upload to digital realms. Imagine aliens living in virtual utopias, indifferent to the physical galaxy. Mind-bending, right? Self-replicating probes add another layer. John von Neumann's 1940s concept of machines building copies could colonize the galaxy in millions of years. If aliens exist, their probes should be everywhere, mining asteroids, surveying planets. Yet, we see no von Neumann machines. Perhaps they're here, nanoscale and hidden, or programmed to avoid contact. Or colonization is impractical, energy costs, risks, or ethics halted. This, "where are the probes?" variant deepens the paradox, suggesting expansion isn't universal. Why not fill the galaxy with machines? Cyclic catastrophes could explain it. Galactic events like gamma-ray bursts from magnet-ars or hypernovae might sterilize swaths of space every few million years, resetting life. Earth's mass extinctions, 5 major ones, show vulnerability. A cosmic one could wipe intelligent life periodically. If civilizations rise between blasts but rarely overlap, contact is rare. Evidence. Ordovician extinction 440 million years ago might link to a burst. This reset button hypothesis makes the paradox a timing issue. Could periodic doom keep the galaxy quiet? The simulation hypothesis, from philosopher Nick Bostrom, flips the script. We're in a simulated reality, and aliens are absent because programmers didn't include them. Fine-tuned constants, quantum measurement issues, and computational glitches like Mandela effects hint at code. If true, the paradox is artificial, no real galaxy, just a program. This meta-explanation, untestable but provocative, challenges reality. Are we NPCs in a cosmic game? Panspermia complicates things. If life spreads via comets or asteroids, as suggested by organics and meteorites like Allende, the galaxy might share a common ancestry. But if intelligence is rare, civilizations are sparse. Directed panspermia, aliens seeding life, could mean they created us but left or died. Francis Crick proposed this, with life's code as evidence. The paradox persists, but with an ancestral twist. Could our origins be extraterrestrial? Interstellar migration's difficulties underscore the paradox. Light speed limits travel, even probes take millennia for nearby stars. Relativistic effects, time dilation, mean travelers age slowly, but home worlds advance centuries. Energy for acceleration rivals planetary outputs. Wormholes or warp drives, theoretical, require exotic matter we can't make. Aliens might conclude exploration isn't worth it, focusing on home or virtual worlds. Our assumptions of expansion may be anthropocentric. What if aliens are homebodies? Let's bust myths. The paradox doesn't prove we're alone, searches are incomplete. UFOs aren't evidence, most are explainable, lacking rigor. Aliens aren't hiding in plain sight, extraordinary claims need proof. And no, the paradox isn't solved, debates rage. The true story, science, speculation, silence, fuels our quest. What surprises you most? The future holds hope. The James Webb Space Telescope probes exoplanet atmospheres for biosignatures. The Vera C. Rubin Observatory maps transients, potentially spotting technosignatures. Breakthrough Starshot sends probes to Alpha Centauri. AI enhances SETI, analyzing petabytes for patterns. Europa Clipper hunts ocean life. Could a signal arrive tomorrow? Might a biosignature change everything? The search continues, full of promise. What does this mean for us? The Fermi Paradox challenges our place, urging caution and wonder. In a silent galaxy, we're stewards of intelligence, responsible for survival. From Fermi's query to SETI's scans, it drives innovation, unity, and reflection. We're cosmic seekers, alone or not. As we near the end, let's gaze ahead. The Fermi Paradox, with its unanswered call, unveils life's fragility and vastness. New discoveries, signals, and worlds will illuminate it. Who's out there? How will we meet? The universe whispers, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into the Fermi Paradox, asking why we haven't found alien civilizations. I hope your curiosity blazes. If you loved this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about the Fermi Paradox? What mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Explorers.